Good evening, everyone. Welcome to the University of Plymouth. I'm here this evening to talk to you or to introduce you to our speaker, Professor Deborah Greaves. And we're here this evening as part of the UK Research and Innovation funded Festival of Research called Futures. Tonight forms part of a series of events happening across September and October, which is a showcase of the research happening across the Southwest. The festival is in its 6th year now, and we're delighted to be joined this evening by Professor Greaves to talk to you about such an exciting and innovative subject. Before I introduce Deborah to you properly, a few housekeeping items. For those of you in the room, please keep your phone devices on silent. However, you might like to keep them handy because there will be an opportunity to ask questions via Slido, and the codes and instructions are on the wall around you here. There are no fire drills scheduled for this evening. However, if there is an alarm, please remain calm and follow the green fire escape signs and congregate on our assembly point, which is in the Sherwell car park outside of the main entrance of the building. Toilets are clearly signposted and available on all the floors. And tonight's talk is also being live streamed on YouTube, and a video will be edited and showcased for others to watch in the future. Without further ado, I'll now introduce you to our speaker for tonight, Professor Deborah Greaves. A Professor of Ocean Engineering here at the University of Plymouth, Deborah's interests include marine and offshore renewable energy and physical and numerical modelling and wave structure interaction. Professor Greaves holds a directorship in the Centre for Decarbonisation and Offshore Renewable Energy and the Coast Laboratory, and is a non-executive director for the Celtic Sea Power plc. Deborah has led many national and international research projects concerning offshore renewable energy in collaboration with industrial and academic partners. She is also a director of the EPSRC £16.5 million Supergen Offshore Renewable Energy Hub. In the 2018 Queen's Birthday Honours List, Deborah was awarded an OBE for her services to marine renewable energy, equalities and higher education. In 2020, she was elected to be a Fellow for the Royal Academy of Engineering, and in 2022 became a member of the EPSRC Council. We're delighted that Professor Greaves is here to talk to you this evening about innovation in wave energy.
Thank you very much indeed for the introduction, and thank you very much for the invitation to talk to you this evening. And thanks for all of you for coming along today on such a lovely sunny evening. So thanks for being with us today. I'd like to talk to you about offshore renewable energy. The title is Harnessing the Ocean's Energy, and I'd like to explore what that means, what different types of ocean energy we can exploit for renewable energy generation, where we are in our research in that, and what we do here at the University of Plymouth. Now, we've had a few issues with my slides, and I think these might be an old set, but never mind. We will go through with what I've got here. So they're the right talk. They might be in the wrong order. But really, what I'd like to talk to you about, first of all, is to think about what is offshore renewable energy, why do we need it, what is it actually, and what are our plans for developing offshore renewable energy, what are some of the challenges and innovations that we need to tackle. I'd like to also give you an introduction to our Centre for Decarbonisation and Offshore Renewable Energy here at the University of Plymouth, and also to our national programme, the Supergen Offshore Renewable Energy Hub. Okay, so this is really all about climate change, how to mitigate some of the impacts in climate change, what we can do to try to do that as a globe. I think we've seen this week a lot of very real impacts of climate change, what's going on in Portugal with the fires and the terrible flooding in Poland, for example. But over the years, I think we're seeing more and more of this. And in fact, it was recently announced that over the last 12 months, for the first time on record, then we've been, on average, over or surpassing the 1.5 degree sort of Paris-agreed limit. So there is a global consensus. I think we can all see some of the impacts of climate change. And the global consensus mostly is to reach net zero. So that means net zero greenhouse gas emissions by the time we get to 2050. And this plot on the right-hand side shows you for the whole of the globe which countries have agreed to that You'll see most of them are in the sort of pale blue colour, so that's 2050. That's the net zero by 2050. A few of those on the right-hand side have gone a little bit early, and then there are a couple on the other side as well, who hopefully will change very soon and make their commitments. So there is a global consensus. We can see the effects of climate change happening, and also it's no longer really seen as the expensive alternative. So the economic argument for climate change is also made and beginning to be more widely understood. So developing renewable energy to help us to get away from fossil fuels that have greenhouse gas emissions and move towards renewable sources of energy is not only going to increase our energy security and help us to get towards net zero, but it's also going to save us money. Okay, so the work of the UK's Climate Change Committee looks at how we can develop pathways, how we can get from here to there, how we can get to net zero by 2050. How can we decarbonise our energy systems, our electricity grid, and all the other sources of energy that we use. And as part of those pathways, there are various different scenarios that they look at. This is all available online if you look up at the Climate Change Committee reports. And the ambition is to have the electrical grid to be entirely low carbon by 2035. You may have spotted recently that the announcements we've seen from our new government have actually upped that and are planning to go for a low carbon electricity grid by 2030. So they've increased the target or brought it forward by a year. The scenarios also show 80% of our electrical generation coming from renewable sources by 2050. But alongside that, it's not just about increasing the amount of electrical generation we have at the moment, up to 80% being from renewables. By 2050, we're also going to double the amount of demand that we have. Because, of course, we're electrifying a lot of our energy systems, cars and other transport, in order to be able to decarbonise. And if you go on a website like this, you can actually see this GridWatch website. You can see live what our proportion of energy from different sources is. So it's a very interesting place to have a look. But if you look at this plot here, this is how we're planning to get from 2020 here towards 2050. And you can see that pink colour, that's the variable renewables proportion. And you can see that that's expanding and expanding through to 2050. Some of those other colours are disappearing, like the unabated fossil fuel generation. And also the other thing to notice is that the number at the top is pretty much doubling. So it's going from 300 up to over 700. So demand's going to increase, and we need to change to renewable sources. So why offshore renewable energy? Well, offshore renewable energy potential is vast. Where we live, we're surrounded by the sea. We can access that. We have the technology. We have the expertise in a sort of naval history and heritage and offshore heritage. It's on our doorstep. And the potential is really vast. The UK is also leading in the technology development for offshore renewable energy. So we have a good position here. And if we can exploit that, then we can effectively generate a good export potential as well, good export market. So it's locally available. If we have our sources of electricity local to us, then that helps with energy security. So there's some numbers there. So globally, by 2050, if we think about offshore wind, you can find almost any number you like. But a big number, 2,000 gigawatts, could be used from offshore wind by 2050. That's a global figure. And the sort of energy that we use, 18,000 terawatt hours. If we think about other sorts of sources of offshore renewable energy, so offshore wind is one, another is wave energy, and another is tidal stream. So from wave energy and tidal stream, then you can see that there's also great potential in terms of the energy that's out there if we could exploit it. And then if you compare that to the global demand, you can see that it's well surpassed by the potential resource that's available offshore. So it's a great place to go. What are we doing in the UK about this? So we've seen the work that the Climate Change Committee do in terms of projecting scenarios. We've seen our strategy and targets along this pathway towards net zero change quite radically over the last few years. So from 25 to 30 to 35 to 50, this is the sort of pathway that was part of the strategy set by the industrial strategy. This is part of the sector deal that came out of the offshore wind sector. And that was launched in 2019. They said 30, 30, 30. They said 30 gigawatts of offshore wind by 2030. Then along came the 10-point plan for a green industrial revolution in 2020, so just the next year. And the target went up by 10 gigawatts. Then just a couple of years later, in 22, we had our energy security strategy, and the target went up still further to 50 gigawatts of offshore wind, and we introduced a target for floating offshore wind, and we'll talk about that in a minute. And then, since we've had our new government just come in, talking about a new approach, setting up Great British Energy, also making some further plans, talking about quadrupling offshore wind by 2030. So now we're going up to 60 gigawatts. So in the matter of 5 years of making projections, targets and strategy, we've gone from 30 gigawatts to 60 gigawatts in offshore wind target. But, have we seen any reason to make that kind of ambitious acceleration of the projection? It's very good to have a target. But we need to have innovation in order to have a chance of making that. Okay, so how do we develop the market and how do we convert those sorts of targets into offshore wind farms or offshore renewable energy farms more generally? So the way it happens is our seabed is owned by the Crown Estate. So the Crown Estate looks after the seabed. They carry out a leasing process, so they lease areas that can be developed, invite private developers to come in, pick a site, decide to build a farm there, and then they need to secure the market, so they need to secure a contract for difference normally in order to sell the electricity. That whole process can take about 15 years to get up to the sort of financial closure. So it's a very long process. So bear that in mind when you see these numbers. But the map on the right-hand side shows you where the offshore wind projects around the UK are at the moment. Where there's a number, I think that means there's more than one project in the blob. You can find all this information out on Renewable UK's website. It's all openly available. And the government runs a contract for difference annual auction that happens once a year. And these are just some of the results for the last 3 years. So since 22, it's been an annual process. Before that, it was a bit more infrequent. In 22, we had 5 offshore wind projects securing contracts. In round 5, we had a bit of a blip. There were no offshore wind contracts secured. And this was because up to this point, we'd seen the price or the cost of offshore wind reduce really significantly. And then we had all of the issues with inflation and so on during this period, and the sector just couldn't keep up with the way the prices were going up. So there had to be a reset, and thankfully in this next auction, it's just been announced a couple of weeks ago, 24, that 9 offshore wind projects were supported. And this is because the sort of cap on the price was increased to account for the fact that the prices have gone up so much. If we look at marine energy, so marine is wave and tidal energy. This is the map for wave and tidal energy, showing you the sites around the UK where there are projects. They're mostly demonstration projects rather than, well, they're all demonstration projects rather than commercial projects at this stage, because wave and tidal energy are at a much earlier stage of development. But you can see that actually there is support for tidal stream projects within the contracts for difference schemes. So in the last 3 years, also since 22, one of the initiatives that was brought in was a ring fence for tidal stream. So some of the value within the size of the pot, if you like, for the offshore wind contracts was put aside for tidal stream. And you can see that that's beginning to grow as well. So we had 41 megawatts, and then we've got 50 megawatts last year, and then this year just been announced a further 28 megawatts of capacity. So this is megawatts, and in the offshore wind ones there's a gigawatt, so there's 1,000 difference in there. So the gigawatt's much bigger than the megawatt, and that also shows you how the offshore tidal stream is really much more earlier stage in its commercialisation. And then also we have a separate pot for floating offshore wind, and we've seen a couple of projects for floating offshore wind secure contracts as well. Okay, so that's the sort of national process. And then if we look a bit closer to home, we can see what the Crown Estate is planning to do over the next few years. They're trying to give some good information looking forward so that people can really plan over the next few years and see what's coming. It's very exciting for us because it's on our doorstep, our local area. The Celtic Sea region is being leased, so the red shapes that you can see there, those are out for leasing at the moment. That's called part of the round 5 leasing, and that competition process is going on at the moment, with developers looking at those sites and thinking about putting bids together to develop projects at those sites. The yellow small shapes that you can see there are test and demonstration projects, which are smaller scale projects, which we'd expect to see happen sooner. And then the green hatched area is sort of the projection of where there could be leasing in the future. So that's not a fixed area, it's just showing the sort of areas that might be developed in the future by the Crown Estate. And as you can see, there's the green bit down here in our area, and then there's also an area in the northeast where there may be floating offshore wind as well. So the leasing's underway at the moment for round 5. That's going to have 4.5 gigawatts of offshore wind, and the future potential is seen to be in this region and also in the northeast. Okay, so now I'm going to just step back a little bit and think about, well, what actually do we mean by offshore renewable energy, and what are the different forms? So I've mentioned already, we talk about offshore wind and tidal energy and wave energy, and I just want to think a little bit about each of those. So first of all, offshore wind. When windmills are not new technology. So we've seen windmills in our landscape for millennia. If you look in that photograph, you can just about see in the back there's some modern wind turbines, but let's bring some a bit closer. So onshore wind turbines on the shore. Some of the issues with onshore wind, they're not always that popular in being close to where people live, or also in very beautiful areas. People aren't always so keen to see onshore wind farms being developed. Also, the potential is not so vast as it would be offshore because of the roughness of the land and the hills and the mountains and the houses and so on. So you get a better quality of wind offshore. But essentially the idea is you're just blowing the wind and turning a turbine. So here's a turbine going round. This one's actually got a battery in it, of course, because we haven't got enough wind in this building. But anyway, so there we are. We're familiar with onshore wind. Some of the issues are around planning, public acceptance, and generally that's it. Offshore, then, as I say, there's more there's an increased resource, if you like. There's better quality and stronger winds, potentially. The public acceptance isn't such an issue because they tend to be out of sight, or certainly far enough away. And also we've seen enormous cost reduction in offshore wind. And we've also seen enormous scale up. So part of the reason we've seen that cost reduction is because we can, for the same platform, we can increase the size of the turbine and catch more air. So for quite often the expensive bit of the structure is the foundation and the tower that the turbine sits on. And so you can make, obviously you need to make that a bit bigger as you make your turbine bigger, but you can increase the turbine, catch more air, have a larger capacity turbine, so increase the gigawatt capacity. And here's some data from LRE Catapult, and you can see the progression or the increase of the size of those turbines, and that's just up to 2025, going from the original windmills there. And I would say the other thing that's quite, that we should note when we're thinking about offshore wind and the price that it's got to, because it's been able to develop from over millennia and also from a very sort of small-scale domestic situation to very, very large turbines. So that's going up to 15 megawatts, and I think that's supposed to be a picture of the shard in the shadow. So these are very large structures, but people are talking about 20 megawatts now as well, so even bigger still. But that scale-up has been achieved partly by, as I say, increasing the sizes of the turbine. But then there was a bit of a price blip last year where there had to be a readjustment. Okay, so then why do we need to go to floating offshore wind? So why do I keep talking about floating? Well, the thing is, this is a map which shows you the bathymetry, or the water depths around the North Sea. And the red bit, the red colour is the shallower water, and the green and blue colour is the deeper water. So I think you can see there, and you can see very clearly why it's the North Sea, which has got lots of offshore wind farms on it, because it's shallower water, and we can sort of almost just copy what we're doing onshore and build it offshore. And we can do that using the same sort of foundations. So we can use piled foundations, or we can use jacket structures, a bit like offshore rigs. And we can use those in relatively shallow water, up to a water depth of about 50 to 60. Some people are even saying 100 meters now, but normally we'd say about 50 to 60 meters. It makes sense to do fixed offshore wind. But, of course, we want more offshore wind. We want to get to 60 gigawatts by 2030. So we need to find some more sites. We need to move out further from the shore. We need to go into deeper water and further offshore. So that's why we're looking at these areas here and up here. And you can see the colours aren't quite so red there. And also in Scotland, of course, there's the ScotWind projects as well around here are also, well, they've been leased now. So we need to develop new floating technology in order to support our structures. So the top bit's the same. We're still going to have a turbine spinning around on the top, but how we support it, the foundation is going to be different. So here's a diagram that just sort of explains that. You can see this is a monopile, so it's just a big pile. And then there's the jacket type of structure. So those are fine in shallower water. Here it says up to about 50 meters, but all of this technology is developing all the time. And then if we go to deeper water, we need to design a floating structure. And these are three general types. Actually, there's probably a fourth, which is the barge, which we'll see in a minute. But the first one there is a tension leg platform, TLP, and it's got taut lines down to the seabed. You can see it's got a very narrow mooring spread. The semi-sub platform, that's got a catenary mooring, so it tends to have a very long mooring spread. And then the spar on the right-hand side, That one's got a much deeper draft than the others, so it uses a very deep draft with a low ballast to create its stability, whereas the TLP uses the tension in the taut lines to help it be stable, and the semi-sub uses its water plane area to stabilise. Now, I was hoping to have a large tank of water here with a little wave maker in it, which is our hands-on demonstration. It's our mini wave tank that we take around to events. But unfortunately, we couldn't get it through the door, and we couldn't persuade someone to run a hose into it. So never mind, you just have to imagine this is floating in water. So this sort of 3-column structure, this is the floating foundation, or the hull for the floating foundation. The water line might be about here, so it's floating in the water. And you can see that when the wind blows and the thrust of the turbine changes, it's going to move around. It's also going to move around when the waves attack it as well, or interact with it. And then how's that fixed to the seabed? Well, it would have a catenary mooring line coming off from 3 points. So that's our floating offshore wind turbine. And so, some of the things around the design for this type of platform are to do with making the structure as efficient as possible. But some of them, of course, are about how we can manufacture it and how we can install it. And if you just look at those 3 there, the spar has got a very deep draft. So you wouldn't be able to build that at a port which doesn't have a very deep draft. So, quite often the infrastructure and the facilities that are available to you will actually drive the design solution that you end up with. Okay, so, and here's some sort of futuristic ideas about innovations in floating offshore wind, the type of structures we might see. This came from the Catapult a few years ago, but there are all sorts of areas of innovation and research and new developments in floating offshore wind in particular. So novel blade structures, robotic crawlers and autonomous drones, so that one of the things we'd like to do is to make it safer to operate and to maintain these structures. We don't really want people to be transferred out and working on them to do inspection and fix things. So we'd like to do that autonomously. And so there's a lot of research going into development of autonomous vehicles and how can they be used for inspection and repair. Then there's some ideas about multi-rotor platforms. This airborne wind idea, that's the kite that you can see there attached to a buoy. It's a little bit like kite surfing, but you have a kite in the upper atmosphere, so it's getting, not the upper atmosphere, but high up in the atmosphere, so you get quite a good quality of strong, consistent wind. And you can put a turbine on the kite. It is being developed. And then we've got these autonomous vehicles again, integration with storage, so how we can integrate offshore renewable energy, offshore wind, with the generation of maybe hydrogen or other types of vector for carrying the energy and storing the energy. And then on the right-hand side, that's a vertical axis floating turbine. We've tended to go to horizontal axis and converge to that, but that's really just because that's the design that's worked onshore and for fixed turbines. As you go offshore, then possibly there's also an opportunity for vertical axis. So those are just pictures, but what's actually happened? This is a plot which shows you the progression of floating offshore wind, including projections made by different countries, and it's in the Global Wind Energy Council, GWEC's report, that was in 22. But you can see from 2007 to 2030, and the light blue bars, those are projections. So this was published in 2022. And you can see the pie chart there. That is the sort of proportion of floating offshore wind. And you can see that the UK, where the sort of teal colour there, we've got most of it at the moment. And the other thing you should notice is that this vertical scale is actually a log scale, so it's not going up linearly. It's going 1 kilowatt, 10 kilowatt, and so on. So it's a log scale. So what have we seen? Well, there's been significant progress in the past 15 years. And the UK is the home to the greatest percentage. So we've got, capacity-wise, we've got 80 megawatts of floating offshore wind in the UK out of a total of 121. And, but everyone is projecting, planning to develop and build markets for floating offshore wind. So there's going to be a lot of it around the world. Here are some photographs of real structures. So these are actual things, not just images. And these are prototypes or demonstration projects that have happened around the place. So this is the first one in Italy, Blue H. And that's actually a TLP. That's a tension leg platform type of platform. Then you might be familiar with Equinor. This is the platform which was first installed in 2017. And I think there are 3 of them in Scotland at the moment. And this is a spar type of platform. Equinor was previously Statoil, so it's a Norwegian company. Principal Power. This one is a semi-sub, so this is similar to this design, the floating platform there. That will have a catenary mooring, and that one is in the Kincardine project, which was installed in 2021, and that one's also up in Scotland. And there are currently 2 others which are in designs in operation in pilot scale. So there's the wind float by Principal Power, and then there's the high wind one by Equinor. So there are just 2 types of design in operation at the moment. Okay, tidal energy. But actually, before I finish on that, I just would say, although there are 2 in development in operation at the moment, we've recently done a review of design for floating offshore wind, and we found 108 concepts being developed. So it's a hugely innovative space with lots of different designs being investigated. Okay, so let's think about tidal energy. What do we mean by tidal energy? Well, tidal energy is to do with the tide coming in and out. And it's not wave energy, it's to do with the tides. And there are 2 different ways that we can extract tidal energy, or 2 different ways that it can be used. The first is tidal range. So tidal range is to do with the change in elevation of the sea surface when the tide comes in and out. So if you put a barrage across an estuary or as a lagoon, and you hold the water back when the tide comes in, then you can let it drain through turbines as it goes out. So you need to impound the water. It's a barrage or a lagoon type project. And the technology for that exists. There's La Rance in France, which has been going since 1960 or something. Tidal stream is a new technology. So it's tidal stream that we really work on more in the offshore renewable energy research area. And in this case, it's a turbine which is driven by the flow of the current. So as the tide goes in and out, it doesn't just go up and down, it actually draws in and out around the landmass of the whole of the globe. And as a result of that, it generates tidal currents. And those tidal currents can be concentrated in some places. So this map shows where that sort of thing happens. So the tidal flow can be concentrated around a peninsula or in between 2 islands as it goes through a constriction. The types of device that we can see, so the one at the top is a tidal turbine, 2 arms, 2 turbines, 1 on either side, and each one has got 2 blades. And this is a monopile. It was actually tested in North Devon. In that case, it's a monopile, sticks out the water. The turbine, as you can see, is out of the water at the moment. That's because it's in its maintenance position. Then it lowers down under the water and the turbines will turn. Quite an expensive way to do it. And then this one is an open hydro, so it's a different type of turbine with an outer ring and the blades are on the inside. But probably the more familiar, the more common type of turbine looks very much like this, a horizontal axis 3-bladed turbine. And, well, I don't know if you can see that, there's a picture of one here. But essentially it's going to have smaller blades and it works under the water. And often they'll be placed on the seabed. But one of the challenges, oh yeah, I've got another photograph, good. There you are. So these are some photographs of a couple of projects. The top one, that's your seabed mounted tidal turbine, classic 3-bladed turbine. Looks a bit different from a wind turbine, of course, because the turbine blades are much sort of fatter and shorter. The density of the water is much greater, so it's got to accommodate those loads. But it can be very difficult to operate, to install these farms and also to maintain them and to inspect them if something goes wrong. So they're on the seabed. We want to put them in a place where there's a strong tidal current. So we need to wait for slack tide in order to be able to get in there and lower the turbine down to the seabed and attach it. And that only happens once a day, so it's very difficult, or twice a day. It's very difficult working conditions. So another solution is this type, which is a floating tidal turbine. So this is a little model that we use to demonstrate again. And there's the turbine. So if you imagine that's fixed, and it would be moored to the seabed again. So it's floating and it's moored to the seabed. When the tide comes in, the turbine turns. So that's, and the advantage of this is that you can tow it into place. It's much easier to install. You can also inspect it on site. You can move the arms up and get onto the device and inspect it. So, but in those tidal projects getting contracts for difference that I mentioned right at the beginning, then some of those are that type and some of them are this type. So both of those have secured contracts to commercialise those technologies. And there are some projects in Wales and some projects in Scotland. Okay, now what about wave energy? So wave energy is not tidal. Wave energy is to do with the waves. So the waves are created by the wind blowing over the water surface. They're quite predictable because they tend to happen after the winds come and after a storm, and they stick around for a bit longer. They're a vast resource, so we have an enormous wave energy resource around the world, and it's close to the demand. You know, most of the cities we have in the world are close to the sea. But wave energy, it's still not really fully commercialized. It's still at demonstration stage. There's a lot of research and innovation going on into wave energy, and it's not really developed to the extent that it's become commercially viable yet. But it has, it has a huge potential. And I think one of the reasons for that, if we go back to thinking about offshore wind, the offshore wind turbine design and that great cost reduction that's happened in the development of offshore wind is partly because it's been able to develop onshore and then sort of step out from there and learn as it goes. Because in engineering, when you're designing new technology and new structures, you need to learn as you go. So you learn from every deployment you have. With wave energy, there's no sort of half measures. There's no domestic scale where you can test it out somewhere where it's really not going to experience the full loading and environment of being in the ocean. So, there's no sort of half measures. And I think that's part of the reason why we haven't seen that same gentle progression of cost reduction in wave energy. But the potential is there. Okay, the other thing about wave energy, apart from it being quite frustrating, and it's not really got to where we'd like it to be, is that it's a really fascinating area because waves themselves, water waves, are very fascinating things to understand and to analyse and to work with. They come they have different frequencies, they come from different directions and different amplitudes and so on. It's a very fascinating area. And for wave energy conversion, how do we convert that energy, that motion, those pressure differentials in the ocean, in the water column? How do we convert that? How can we design a machine that can convert that energy and make some electricity? There are many different ways to do this, and actually quite a lot of different ways that people like to characterise or classify the different types. But here I've got them in just 3 general areas. So the first one is an oscillating body. This is a heaving buoy, so it's attached to the seabed, it's afloat, and it's going up and down when the waves go up and down. And if I had my lovely demonstrator tank here, you'd be able to come and actually do that and make a little light come on. But never mind, you just have to imagine. Other types of oscillating bodies, so there's a flap, the middle one. That can be on the seabed, and it's basically a hinged flap, typically in shallower water. And then the right-hand one is the articulated type of wave energy converter. And this is an example of that. And some of you may remember Pelamis, which is a sea snake, which was tested and was sort of the face of wave energy for quite a long time. That was a long set of 5 cylinders connected together, and each one would move independently and with a sort of power takeoff in between them. This is a hinged raft, so it's a very similar concept, but it's essentially 2 different, these would float on the water surface, and they would move relative to one another in the waves. These things are just the anchors and the moorings there for when we put it in the tank. But it's very simple. So we can have a power takeoff, some sort of hydraulic system, generator in the hinge that is used to make the electricity. And then there'll be a cable that takes that back to shore. Okay, so those are oscillating bodies, and there are various different ways that you can do that. The middle line are oscillating water columns. And in this case, you've got, well, let's look at this one. This one would be built into a seawall, and there's one in northern Spain, which is a commercial project, which has been running since 2020-ish, and provides the local town with electricity. So you can build these into seawalls or breakwaters. And essentially, it's just building a chamber with air inside it on the side of your seawall. So you can see the water inside there. It's open at the bottom to the sea. So as the waves interact with it, then that water column is going to go up and down. It's going to act a little bit like a piston. And with all of these things, you can design them to resonate or to react in a maximum way with the incoming waves, if you understand how the wave frequencies work. And then at this point here, there's going to be a duct, and there'll be a turbine in that duct. So that's an oscillating water column. The water column is oscillating. It's actuated by the wave action. What it's doing is it's kind of moving up and down, changing the volume for the air above that water column, and that's being driven in and out through a duct. Now, this is actually an oscillating water column. This is a floating type of oscillating water column, also a point absorber. And this is something that we used to do some experiments with. So you might imagine the water lines here. So that bit is the ballast, so that's floating down in the water just to keep it upright. And inside here, this is the air column. It's open at the top. So the water line inside that central column would be about here when it's at rest. And then when it's interacting with the waves, that will go up and down. We can put a turbine in the top, and that's how we generate the electricity. So that's also an oscillating water column, but it looks very different from the type in a seawall. And then finally, there are overtopping types. Again, this could be fixed or floating. And here, we're just capturing the water as it overtops, normally sort of channeled through over a ramp. We're collecting that in a reservoir and then allowing it to drain over a low-head turbine. So here are some photographs of those in reality. So this one is the hinged raft. This is very much like this, and it's developed by a company called Motion, which is actually it's like a new generation of the Pelamis type of device. The oyster is the oscillating flap, and then here you can see this is the breakwater in northern Spain that I mentioned in Mutriku. So it's still under construction here, but it's been working. It's been finished for a number of years now. There are a number of I think 8 different oscillating water column chambers and turbines there. Right, and then those are the spar. These are a bit like the spar buoy in our tank. And there are a couple of examples of the overtopping type, the wave dragon, and this slot cone, which is a fixed device. So there is a huge untapped resource of wave energy. This is a map of the globe, and you can see the mean power density along the bottom there. The red is high, but it's all over the globe. It's abundant. We've done some work to review the resource for the UK. So this is a map of the UK, and just showing some of the areas where wave energy has been tested or demonstrated or investigated. And then there's a review there where we developed a roadmap for wave energy and proposed some of the innovations that might be needed in investment to try and get it to the next level. But there are some challenges with wave energy, as I say. But there are also some real benefits. So I just want to have one slide where we think about the system of electricity from renewable energy, variable renewable. So renewable sources of energy are always going to be variable by their nature. And the point of this is to show that actually we need a diverse mix, and we need them all if we've got a chance to get to 2050. So this plot is the demand across 1 year, so an average from January to December. So roughly for the UK, we tend to use more energy in the winter than the summer. Obviously that will be different for different parts of the world. So this is something which is very location specific, variable. If we look at the wind generation for the UK on average, then it kind of follows quite well actually the demand, but there's lots of gaps in there. If we look at solar for the UK, it kind of flips and is higher when we're in the summer, obviously, not so good in the winter. Tidal is very predictable. Of course, the tides come in and out twice a day, so we can predict forever what the tidal cycles are going to be. And then wave energy, if we plot that on top there as well, we can see that we've got a very high potential resource, particularly coinciding with peak demand. But the point of this slide really is to just show that if we are going to move, we are going to move to renewable sources of electricity, they will be, by their very nature, variable. And so in order to make sure that we have electricity when we need it, so we have energy security, we need to have a diverse mix of those renewable energy sources. And if we have them all together, then we have a much better consistency, we have much better energy security, and it's cheaper because we don't need to over-provide, and we also don't need to spend so much on storage. Okay, so I'd like to just say a few words about the Centre for Decarbonisation and Offshore Renewable Energy here at the university, and I'll also introduce the Supergen Hub. So our centre is an interdisciplinary centre where we bring together and work together on some of the big challenges in offshore and decarbonisation, sort of focus around net zero, energy security and clean maritime. And it's a way of sort of bringing together the expertise, the facilities, working together with external partners, and it's an interdisciplinary research area. Some of the facilities we have at our disposal, so I've mentioned the wave tank, I'm going to tell you a little bit more about that, but here's an image of it in our coast lab in the marine building. That's been going since 2012 now. We also have our cyber ship lab, where we look at some of the cyber challenges around within the maritime environment. And of course, offshore farms, offshore wind farms, offshore renewable energy farms are part of our critical infrastructure and have a need for to be kept secure. So there's a new lab, the Crown Lab, which is looking in particular at the cyber security challenges around offshore wind. We have a whole fleet of autonomous vehicles and lots of work looking at marine autonomous systems. We have a new maritime simulator which is a very clever simulator, which is possible to do some very complicated, test out complicated installations. A wind tunnel and a hexapod for shaking things about. And then another exciting thing we've just launched recently, which is a blown wind system in our wave tank. So that means we can do wind loading on structures as well as wave loading and current loading. And that's ideal for floating offshore wind, of course, where we want to see how things will respond under those combined loads. So those are some of the facilities that we have here in the university that we can apply to this research. We're also planning and asking for more. So this is a proposal we're working on for a national infrastructure, which would be a floating laboratory off the Sound, and it would also have a digital twin or digital connectivity into other structures. And the idea eventually is that you'd be able to do an experiment here in Plymouth Sound that could answer the question, in my offshore wind farm, wherever it is in the world, what happens if I change this interconnector, or I change this mooring line, or I change this dynamic cable for a different one? What effects is that going to have? So that's the idea for that. But a lot of the work that we do at the moment, of course, is in the laboratory in the university. So I will show us a few slides of that. I don't want to go too late, so I'm going to go a little bit faster for some of these. But here's a little video of a 70th scale floating offshore wind turbine in the Coast Laboratory. So this is at 70th scale. It would be at full scale about 100 meters across the base. And you can see at the top, that doesn't look much like a turbine, does it? That's our hardware in the loop system. So instead of, this is the system without blown wind. So instead of blowing wind at this structure, we can apply some thrusters here, which will generate the same thrust that you would get from the turbines turning. And that happens by, during the experiment, we measure very precisely the 6-degree of freedom motions. Those little dots on there are doing that with a remote camera system, running a very fast code to work out how the different pitch angle will affect the thrust on the turbine in the real situation. So why do I want to do that kind of thing? Well, as I mentioned earlier on, there is a lot of innovation to do in offshore wind and all areas of offshore renewable energy. This is a YouTube of a French floating offshore wind platform. This is a barge type, so it's slightly different from the others you've seen. But this just shows the sort of loading it's experienced in, and these aren't really storm conditions. It's not a big storm by any means. This is the type of constant battering that these structures need to survive. And, you know, unlike a ship or something that can just move out of the way and avoid the storm, these structures that we're putting in the sea need to survive, and they need to stay there. So we need to help them design. We need to test out new innovations. Here are some experiments in the lab. If you look very carefully, you can see there's a snatch happening. So this is looking under the water, from under the water at the floating platform, a little bit like that. These are the chains, and you can see it from the air at the top, and then another underwater view on the other side. I might just see if I can play that again. And what we're trying to do is, yes, did you see that? Get that line to snatch. So we'd really like to avoid that in reality. So how can we design sophisticated or new materials in our mooring systems to prevent that sort of thing happening? So we do a lot of research and development with offshore wind, looking at design loads, load cases, new types of structure, and mooring system. We also do a lot of research in wave energy. We're very interested in investigating new concepts and how we can also design them for extremes. Because, of course, the thing about wave energy machines, I mentioned how they don't get the chance to sort of develop in a gentle, progressive way from onshore. The other thing is that with a wave energy converter, we want it to be able to move around a lot in waves, except when the waves get really big, and then we want it to survive those waves. So it's a really complicated design challenge. So one of the things we've been looking at is new concepts for wave energy using flexible fabric structures or flexible structures. And some of the advantages there is that they can be lighter and smaller. We can use a whole range of power takeoff types. They can deform to accommodate high loads. They can be co-located with offshore wind farms. And the image on the right-hand side is an example of a type of wave engine inverter we were developing with a flexible bag, which is air-filled, and you can see it's going up and down in the waves. And then there's a flexible hose at the top there, which is connected to a rigid chamber on the platform. So the air, as the shape changes for this structure, the air is pushed up into a rigid chamber, and the air spring of the compression gets it to come back again. So we're doing further work to develop this further. This is an example of a progression of that using a different type of device. And one of the design challenges for the right-hand device is you can get a lot of fatiguing in this material, and it can fold and crease in places that you don't expect it to, which can cause problems. So we're doing some work now where we're using origami theory to help us to design the structure so that it deforms in a very predictable way, and that we can understand how it's going to behave. The video worked. So working with a team in Oxford as well, and with some specialist origami design, and you can see there we've been testing that in the ocean basin as well. Okay, and then here's another little video showing the hinged raft type of device. So this is a bit like the pink one here, and the motion one that we saw in the sea. We've been doing a lot of work with motion. You can see a wave coming now. So this is a design wave. So it's a single wave that we've designed in the tank, and we can just, it's a small, when we say a single wave, it's a small wave group, but it has a very large wave in the middle of it. And the idea is that we can prescribe the wave which will create the largest response, and that's what we're trying to do in developing these design waves. Oops, gone the wrong way. Then another area that we've been looking at is the development of arrays. And an array is just a group of wave energy devices. I wanted to show you this video because it's this model here. So here we've got 5 different oscillating water columns floating around, and you can see the yellow bit under the water. So these are 5 oscillating water columns, and what we're doing in this project, which is a European-funded project, we were looking at whether we can reduce some of the costs. So with wave energy, it's a lot about trying to find ways to reduce costs. We're now going underwater and looking underneath, and we want to see if we can reduce costs by changing or interconnecting the moorings in different ways and reducing the overall number of moorings. So here are the 5 devices bobbing around, and you can see these are floats, these are interconnecting lines, and there are some masses there as well. And in this experiment, we started with 5 of them individually connected to the seabed with 3 moorings, and then we connected them together, and we started to reduce the number of seabed connections. Anyway, it gave us some very interesting results and showed that you could really reduce the overall cost of that array without compromising on the power performance. So that was quite surprising. So that's just a snapshot of a few of our experiments. I'd now just like to introduce the SuperGen Offshore Renewable Energy Hub. This is a large program of research that we are running here from Plymouth. It's an investment from the UK Research and Innovation, Engineering and Physical Sciences Research Council, and they've invested in us to the tune of 16.5 million since 2018. And we have this team of universities that we're working with, logos along the bottom, and the remit for the hub really is to try to bring together people working in offshore renewable energy from academia, from industry, from policy, and talking to groups like this, talking to people about offshore renewable energy, to think about what we can all do and how we can get engaged with it and understand it better. We have started our sort of next 5 years of funding, which started in 2023, and we're really focused around some of these challenges in the middle there. This phase, or where we are from 23 to 27, getting towards 2030, and those very ambitious targets, it's all about upscaling, increasing the competitiveness, because this is a global market, sustainability, so looking at circular solutions, thinking about critical materials, recycling and end of use, and streamlining processes, using those autonomous systems and data to speed up some of our knowledge generation around the platforms and the way they behave. Some of the things we've been doing, these are just a few of the highlights of the hub. So we work very closely with industry. We have some core research we do. We have flexible funded projects that we run. We run a call each year for 4 years, and we have industry partners working in those. We produce policy briefings. We often go to COP. And we do support early career researchers. We've got a large, vibrant community of early career researchers. We invest in their research. I've already mentioned the flexible funding. In terms of our engagement across the UK, the 72 universities have engaged across the UK with the Supergen Hub, so we're really broad reach, and we're working with the key people. And a very important area for us is thinking about equality, diversity and inclusion, and how we can improve the diversity, not just of the energy sources for offshore renewable energy in our future grid system, but actually for the people that are working there. And so we do quite a lot here as well in the processes that we take in running our competitions and supporting our researchers and so on. So if you're interested in finding out a bit more about offshore renewable energy, we've got, you can look at our website, and you can find quite a lot of information on our research landscape. So we've tried to create this web tool which summarises a lot of information at a sort of high level, and then in more depth around the whole landscape of offshore renewable energy. So just using this platform, there are 8 different themes of research areas. And within each of those, there are a number of research challenges that have been identified. If you click on there, and then you see these buttons appear, you click on the button and you can find out some more information about those research challenges. So some sort of high-level information about the challenge and the context. And then if you go into the Delve Deeper button, then you can find more information and links through to research papers and websites and projects and so on. And it's an open platform where if there is a project that you know of that's not on there, we'd like it to be uploaded, so it can be, you can do that. So the research landscape, we hope, is a valuable tool. Very much encourage you to explore that if you want to find out more about the area. I also mentioned that we do generate some policy briefings. And as Rosie will know, we are very busy at the moment, just finalising our latest policy briefing. So this is our Outlook 24, and the reason, 2040, and the reason we're thinking about 2040 is because 2030 is really very close now, but 2040 is a little bit further away. 2050 is too far away. But the things that we do now might have a real impact in 2040. So thinking about the research and the innovation and the activities that we're doing now, it just gives us a more immediate frame. It's not too far away so that we just don't think about it, but it's not too close that we also just give up. So anyway, look out for that. It will be launched next week, hopefully. Okay, and some of the things we're thinking about in there. So I mentioned earlier on the Climate Change Committee and also some of the scenario modelling. And here are a few examples of that scenario modelling, just thinking about the offshore wind deployments and are we on track? Okay, and if we sort of extrapolate from where we are now through the pathways, these different colours are the different energy system pathways that have been developed by National Grid. Then there are various different lines, but they all have a very steep slope in this part of the line. By 2040, we're going to need about 100 gigawatts. Are we on track to get there? Well, actually, not really. Not if we don't make a change. So what we found is that we need to increase the rate of development of those projects by 4 times to have any chance to get there. And we need to increase the volume by 7. And of course, tidal and wave. This is wind, offshore wind data. Tidal and wave will be very similar. Business as usual, not an option. Well, that's not the easiest way to get there. So we need to do something different. And we've sort of used the idea of climbing a mountain to get to net zero. It's very challenging. It's very steep. We don't really know the route. So we know we have to do something different to get to net zero by 2050. But it's not just about getting to net zero. We need to get there in a way that's fair for people, that's just, so we can see a just transition, and then we don't have people getting left behind and left out. We need it to be secure. We need it to be sustainable. So we need to think about the planet and our use of resources while generating these resources. And of course, we're doing all of this in offshore. Well, we had some good reasons for doing offshore renewable energy, but actually it's a very busy space. So the ocean is already very busy, and there are plenty of users. So we need to think about how we do that in harmony with other users and with nature. So this is where work of all of us, but actually we're focused within the Supergen Offshore Renewable Energy Hub, of course, directing our research and innovation to help us get there, scale the mountain and get there in a safe, secure and sustainable way. But of course, we all have a role to do this. So we all need to think about, we all need to think about offshore renewable energy. We do. We need it for our future, and there's something that we all need to do in that. So partly to do with understanding, communicating, and there are many different disciplines and aspects to take up. So what does the Supergen do? We, through our research and innovation, hope to reduce the scale of the task, help design the best pathway, and to also train the team and align the stakeholders. So we run masterclasses and training within our hub as well. And we want to get there in a just, secure and sustainable way. Not only do we need to do it 4 times faster and 7 times more, but we also need 6 times more people as well than if we carry on the same trajectory, that is. So we need a much increased workforce. So where are the careers in offshore renewable energy? Well, actually, many different disciplines are needed to build and design and operate and plan for an offshore renewable energy project. So there are opportunities for everybody. By the way, we have a master's in offshore renewable energy here. Some of you might be master's students, and thank you for joining us. We're in the middle, thank you. And of course, the other thing we try to do is not just train master's students and undergraduates, but we want to reach out and communicate to the future generations. So one of the things we've done with Supergen is produce this book. If you're interested, if you know someone who'd be keen to read that, then please do get in touch. We produce these are targeted early readers. They've gone into all the primary schools in Plymouth, and they're available from us. We've also translated it into Welsh, and this is partly because of the work we're doing into Wales through development of the Celtic Sea area as well. Okay, so I was asked to finish at 7:10, I think. So I've just about dead on that. I'm now going to deafen you all because I can't resist to just show you a little, well, I think I'm going to deafen you, it might not play the sound, but show you a little clip from the opening of the Coast Laboratory, which some of you will have seen, some of you may not have seen. Opened in 2012. It's being played as a musical instrument. It's an organ. So the conductor is controlling the computer, which is controlling the waves. The waves are being measured, and the signal is being synthesized into sound. Did you catch that? I think that's enough of that. Right, thank you very much. Sorry.
That was absolutely brilliant. Thank you very, very much, Deborah. And spot on, it's 11 minutes past, so brilliant. I've had a lot of questions come in via Slido, so I'm going to actually start there, and then we can take some questions from the room as well. So let's start with, how does the electricity generated by the floating offshore wind turbines get back to the shore?
Yes, very good question. So the turbine generates electricity, and we need to get it to shore through a cable. So the cable will come, a bit like the mooring lines do, the cable will come off the platform somewhere and then be taken along the seabed. But it is it's a different challenge for floating offshore wind from fixed offshore wind. Fixed offshore wind is a little bit easier to get that cable down to the seabed. When the thing's floating, the cable's going to be dynamic. It's going to be moving around a lot. So that is a real challenge. The design of dynamic cables for floating offshore wind is a really hot topic area for research and innovation.
Slight lead on from there. How much damage does installing wind turbines at the sea cause to the seabed? Is that a concern?
Well, how much? Yeah. So if you think about the footprint of floating, was it about floating? It's floating rather than fixed, is it, or is it both?
Both.
Both. Yeah. So I mean, for a fixed turbine, then you're going to do a pile, a monopile, or maybe you do some drilling in a confined area. For a floating offshore wind turbine, you need to anchor the systems onto the seabed. If it's a catenary system with a chain along the seabed, that might have a longer, larger area that the chains interact with the seabed. A taut moored system might have a narrower mooring spread, so less area that it's interacting with. But obviously, there's going to be some interaction with the seabed as a result of anything that we any infrastructure that we build offshore. So one of the really important areas of research, of course, is to understand that, to understand how we can minimize that and how we can make sure that we're not having an impact on the biodiversity, the communities of biodiversity that we need to protect within the ocean, the marine environment.
We had one more sort of follow-on for that about marine animals. Are they particularly impacted by the development of the offshore energy?
Well, there's been a lot of research in the impact with various species, so whether it's marine mammals, birds, fish stocks, and benthic communities. Yes, there's a lot of research there. It's a bit like I was saying in the beginning, with engineering, you need to do it to find out. And so it's very difficult to have the evidence if we don't have very many farms out there yet. But there's a lot of evidence coming from fixed offshore wind. So I think we know pretty well a lot of the potential mitigation factors for fixed offshore wind. There are some questions that we still don't know the answer to for floating offshore wind, and so there's quite a lot of research being targeted into that area now. But as I say, quite often for these things, when you're putting new technology into the ocean, you can do as much as you can with modelling, with experiments in laboratory, with developing models to try behavioural models connected to physics models to try and see how these things will be interacted. But actually, you need to get that data from the real deployments in order to fill in your understanding of how well it works. What the actual impact is, and so typically you take a sort of an adaptive management approach. Okay.
Thank you. Are there any questions from the room?
obstructing ocean views or anything like that. I'd really love to hear like how you personally would kind of navigate those conversations and like hold your ground as like a scientist in this very budding field.
Yeah, okay. Well, no, I think that's a very good question. I think the one about the impact on the marine ecosystem, there is ongoing research in that area. It's a very, we're gathering more and more information. But of course, these areas that are going to be developed for offshore wind farms or wave energy farms or whatever it is, often they'll be no longer fished in the same way. So they can become more of a sort of a nursery replenishment of stock area. So they can enhance the biodiversity, although they may displace it. So that's something. And then, of course, well, what does that mean if it's displaced? What does that mean for, is that a problem? And of course, the other thing to remember is this is all within the context of climate change, which is happening and displacing and changing the way populations are found in the sea now anyway. So there was some interesting work done recently, I think it's Dasgupta et al. Or somebody who, a few years ago, where it looked at this and it really showed that actually the impact of climate change is going to be quite a lot worse. And we need to obviously try to design and understand as much as we can about the potential impact, but we also need to take a balanced view of that. And I think thinking about community level impacts rather than individuals. A lot of the press will be about individual impact or an event. But what's the actual impact on the community? That's the important thing. And then in terms of public perception, you mentioned that is it in view? Yeah, well that's tricky, isn't it? I think we all need to recognise is that as a population, I think what we all need to recognise is that in order to get to 2050 to be decarbonised, to be able to mitigate climate change, there's going to be a lot more electricity around. How do you transport electricity? We've got to get it from A to B. So, we do have to face up to some of those challenges. I think just there. It's something we all have to understand a bit better. Yeah, go ahead.
I was just going to carry on with that. There's a huge potential for generating electricity offshore. The problem is getting it back because the use will be onshore. But are the parallel projects going on about increasing the infrastructure of the grid? Because without that, you won't be able to bring it ashore, plug it into the grid, and also with storage. So are there parallel projects going on looking at infrastructure development and storage protection?
Yes, absolutely. So the Supergen hub that we are running here in offshore renewable energy, there's a sort of companion one which is in energy network. So that's looking at all types of energy network, whether that's electrical energy networks at the grid and how that might develop in the future, how that might change. When we've got a much more distributed system, we've got much more distributed power production coming from lots and lots of small sources rather than a few very large ones. Or whether it's around the gas network and also alternative vectors. So there's quite a bit of work looking at green hydrogen. So we know that we're going to need hydrogen for some of our uses in the future. How can we make sure that we're developing that in a decarbonised way? So we're looking at the integration of green hydrogen with offshore wind. And then there's a question of how that hydrogen gets used. So there are still many sort of questions that are open, but where is the market for hydrogen? Is it in fuel cells for cars, for large heavy vehicles, for marine transport, whatever? That there are still quite a lot of possibilities being explored. So, yeah, in terms of getting the electricity back to shore. One option is to have a cable from your farm. You have a substation out with your farm and then a cable to shore. Then you've got to get it onshore and into the grid system somehow, distributed to people's houses. And then another option is to have an entirely offshore, off-grid, potentially, offshore wind farm, which maybe is just producing hydrogen. And then that's being transported as a liquid or so or as a gas. So there are different things being investigated. What we do know is that the electricity grid is going to be different from what it is today.
Sorry, it's slightly two-part, but when you were mentioning the kind of potential locations of projects, could you maybe comment on what the kind of prerequisites are? And you also mentioned how a lot of this Crown estate is leased. In terms of how someone who's pitching a project there, is that lease amount restrictive to people looking to kind of invest in this area? Is it a problem for people looking to start these developments, or is that less of an issue compared to other practice?
Okay, I think there's lots of questions there. So just going to the leasing question. So I think the way it works is different in different parts of the world. So for the UK, it's the Crown Estate that runs the leasing process, and what they've done for the Celtic Sea areas, they've done a lot of pre-work. So they've done a lot of work in working with other stakeholders and in collecting data in the area to work out where might be the best sites to use, which might be the best sites to use. And then any developers can, bid for those sites. The way that's working at the moment is that as well as bidding for the site, they're also making a proposal for how they might add social value to the area, to the local area, and environmental enhancement. So those two things are also being considered in the selection of the projects that go forward. But I think, inevitably, price is always a large part of that selection, and that goes for the contract for difference as well. And then what was your first question about where to choose a site? Or?
Yeah, what are the kind of prerequisites you're looking for in terms of where you said, I understand that kind of there's a wind and wave availability is going to be key there. Are there other factors considered as well?
So I suppose, yes. I mean, you look at the resource. So depending on whether it's wind, wave or tidal, the resource is the first thing. Then you might look at, other for a particular area, what are the other users? So is it heavily fished? Is it in the middle of an important route, shipping way? Is it a marine protected area? Is there a port available? Where are you going to do the manufacturing and the installation from? All of these sorts of things. And then, of course, the grid. The grid's quite important as well. So will you be able to get a grid connection, and where's that likely to be? So there are lots of things, and it'll work slightly differently in different countries.
I'll jump back onto Slido if that's okay. There's a few on here that I'll answer. I think they come in online as well. You mentioned that offshore renewable energy transition needs to be done in a way that minimises harm. Oh no, sorry, wrong question. It seems the main reason that harnessing wave energy is so difficult compared to turbine is that you require a much more complex system of movements compared to relatively simple circular rotation of a turbine. Is the approach ultimately doomed? Like Palamis? Is that how you
Palamis,
say?
Yeah. No, of course it's not doomed. We just need to... I mean, the potential is huge. There are technologies that work. They just work at the wrong price at the moment. So we need to find the right market. And that market might not be, competitive with floating offshore wind in the UK at the moment. It's more competitive with floating offshore wind than it is with fixed offshore wind, because floating offshore wind's still, obviously, at the moment, a lot more expensive than fixed. But there are markets where wave energy does make sense. So, for example, in offshore areas where it's being used commercially as a charging point for offshore infrastructure, to power aquaculture farms, to decarbonise offshore operations, and also in small island development states. So We're working on a project at the moment in the Maldives where there's actually a hybrid system, which is floating solar with wave energy integrated. So it's a platform that is doing both in one go, and that's being deployed actually as we speak in the Maldives. So that's an exciting project. So yeah, there are different markets that could work. And then, you know, eventually if wave energy is allowed to develop in that way at a sort of smaller scale, then eventually it might there might be a strong pathway to utility scale, which is where we'd like to get to.
Great. There was 2 questions actually about the combining of marine and tidal and offshore and waves. You've kind of touched on that there as well. So
Yes.
brilliant. Should we take another question from the room? I saw a few hands go up. Oh, sorry, just behind you in the blue T-shirt.
Do you use any of the information and data that was gathered due to the offshore oil industry? Because some of the things which you're doing, or like mooring systems, that has been done 40 years ago, and I believe it was rather successful because they didn't drop too many. And the same with the business of marine growth, because all the offshore platforms had huge fish populations around them. It didn't matter what you did, there were fish there.
Yeah, absolutely.
Mainly because nobody was allowed to fish off a platform.
Yes, yes. And they tend to aggregate fish. So if you put something like that in the water, it tends to be an aggregation device. So yes, of course, a lot of this technology is absolutely directly from the offshore technology. So the TLP, the semi-sub with the catenary mooring, and the spar, they're all offshore oil and gas structures. The difference is in offshore oil and gas, they're enormous, they're massive, and the mooring system is a relatively smaller proportion of the overall cost of the project, whereas floating offshore wind, what you're talking about is multiple hundreds of these floating structures where the mooring system, the cost of the mooring and anchoring system is a much larger proportion of the cost of each device. So it's a very different model. Yes, the technologies and a lot of subsea technology is very well understood and well known, but there are some things about the design which is different, and also the dynamic cable, I think, is again, you know, something with a very large offshore oil and gas platform. You aren't expecting it to move around be quite as dynamic as a floating turbine would be. So there are some different design challenges, but there is an enormous amount of knowledge and all of the design standards, of course, and the basis for these offshore designs come from the offshore oil and gas industry. And I think the other thing is to say that the data is also, I think, you know, there are various bodies that are trying to put together the data and enable it to be shared across different sectors. Now, as you probably know, that's always a huge challenge, but there are efforts to try and coordinate across sectors of offshore energy, which is good.
Have you any idea why we haven't gone for, like the oil industry went for bigger and bigger platforms, why the floating wind turbine hasn't gone to, I use the statement of VLCC size just for the sake of it.
Yeah. Well, actually, we are doing some research in looking at very large floating structures. Same sort of idea, but the thing with wind turbines is they need to be spaced. You know, you can't have a turbine right behind the next one because there's a wake behind the turbine, and it'll affect the power production of the turbine behind it. So the spacing of the turbines is quite important. So yeah, you do need to have a very, very large structure in order to get the spacing. I mean, typically you're talking about a rule of thumb would be 7 diameters of the turbine, and these turbine diameters are sort of 200 meters. So you're talking about a very large floating structure, and then the economics of that relative to having multiple ones.
VLCC.
Yeah, exactly.
Right. In the spirit of sticking to Deborah's very good timekeeping, we've got time for one more question. I think a gentleman here in the shirt had his hand up.
This is a totally technical question. I'm thinking about tidal energy. And you see tidal energy, all these big turbines going like that. Why aren't they going like that?
Yes.
You can make them far bigger, and you can use the water which is under your bridge. That water goes in and out, in and out. The energy is right.
You're talking about a vertical axis turbine rather than a horizontal axis turbine like this one. And one of the slides I showed had a vertical axis turbine on the right-hand side, and I was saying that we were talking about floating offshore wind then, and I was saying actually, you know, it might be a good solution for floating offshore wind, but we've sort of gone down the route of horizontal axis, so we've got the cost reduction there, we're kind of stuck on that. You're suggesting this for tidal, and you're right that there are vertical axis solutions. In particular, so the horizontal axis one tends to work better in the situations where we've got, you know, a tidal flow, but they're also used in what they call in Canada and in the States the run of the river. So you can have your vertical axis turbine sort of sticking out of the river, and it's driven by the river flow. I think, you know, there are some issues with the design of those types of platform. They don't start so easily. I think when you've got the thing with the tidal current, of course, it changes direction. So I think that can be problematic with that type of turbine. And, you know, it's probably the main reason is really just that, you know, it's like the old video VHS versus whatever. It's, you know, this is the one that's seen the most development and cost reduction.
The thing with vertical axis turbines is you need depth. With the tidal flows, there's much more width and depth usually. Turbines spin very fast. A large horizontal one goes slowly.
Yes, no, and yeah, well, they are being developed as well. So there are a number of demonstration projects. None of the ones that have got CFDs in the UK. There is one, a very interesting, something called a tidal kite, which is a completely different thing. It's actually a kite on a... Yeah. Have you seen that one that sort of goes like that underwater? But yeah, the vertical axis ones I've mostly seen being demonstrated in China and Canada, I think.
These are all very small little affairs. I was thinking about a machine with about 5,000 square meters of blade sitting in the Bristol Channel or in the Thames estuary or in the Firth.
Yeah.
There's so much energy going in and out there, and nobody's sticking it.
Yes. Yeah. No, I mean, there's still room for new ideas. Of course, one of the advantages of the turbine on the seabed is that it's out of the way for shipping, so you know it's not a problem. So something that comes through the water service can be more of a problem. So yeah, it's a balance, you know, between the different features of those sorts of platforms and the site that you're at. Okay.
Thank you so much. If there's any other questions that you're desperate to have answered, I'm sure Deborah won't mind staying for a couple more minutes at the front. But if you join me now in thanking Deborah again for her time.
Thank you.
And if I can trouble you for one more minute to fill out the evaluation on your desk, please. It's really important for us to take this back and then secure funding going forward. So if you can fill those out, that would be fantastic. And yeah, thank you again for joining us this evening.